excuse me, where our data comes from. We're going to look at a few of these slides here, trying to make it big. There we go. Okay, so the carbon cycle. So first we want to look at the amounts of carbon flowing between, or sorry, the storages of carbon. So you can see the storages here in parentheses. And the largest storage actually being the deep ocean. Of course, the ocean making up 70% of our planet. That plays a role. And then we want to look at the flows too. So you can see on the left side here we have 60 coming out from the microbial respiration, another 60 coming out from plant respiration, and then also 120 coming in from photosynthesis. So that's actually balanced. Same coming in and coming out. And then we also have 90 coming into the oceans through photosynthesis, and then 90 leaving the oceans through decomposition. So it seems pretty balanced too. But wait, there's also this too sinking down here. So oceans are actually fixing carbon, we would say. Fixing carbon is when you take it out of the atmosphere and you put it somewhere else into another storage, like say the oceans or into the ground. That's carbon sequestration. And then we want to look at the same cycle with humans added. So humans are shown here in red. So we can see of course, burning fossil fuels is the primary human emission. But we also increase photosynthesis by growing farms and crops. Also by, making the climate warmer. The growing season has increased in some places, but you can see this is still out of balance, right? Oh, but we're also adding more carbon to the oceans. As we add more CO2 to the atmosphere, a lot of that just naturally gets absorbed by the oceans, which then become more acidic over time. That's why they talk about ocean acidification. But still, if you add these numbers up, right, we got +2, +3. The system is still not balanced. We're still putting more into the atmosphere than is cycling back out of the atmosphere, and that is why the climate is warming. Pretty simple stuff. Okay, so now we have a zoomed-in system of the Great Lakes region. I believe, I thought I saw this was like in Ohio or something. Oh yeah, Ohio Sea Grant. They're not by the sea. What are they, funny? Anyway, our first task, I believe, is to look at where the most carbon is stored. We can see 1% in the leaves, 40% in the trunks and branches. Makes sense, there'd be a lot more there. 1% in woody debris. And then hopefully you find, wow, actually most of the carbon is in the soil in a forest. And so that's just like Mike says, right? We don't grow crops, regrow soil, and the soil grows crops. Just like in this forest, the soil is really providing everything else for the whole forest. Our next one is to look at the soil respiration compared to the net photosynthesis, right? How much carbon is coming into this system, how much carbon is leaving this system. And so we see 2.9 tons of carbon per acre per year entering the system through photosynthesis. And that's after respiration, right? Net photosynthesis. Some of that carbon doesn't enter the system because it's just lost during plant respiration. And then 2.2 lost to soil respiration. So the question is, which one's greater, where you have more coming in than going out? So what happens to all of that carbon that's going in? Well, it's actually stored in the soil. Here it is, 0.7 is the difference between those two. So this is, at least in a forest, the breakdown of carbon. So in our situation, we're going to look at basically data of soil respiration in this forest throughout a whole year. So what is actually happening that produces CO2? So just like we saw in this last one, we have respiration. So all these microbes and actually macroorganisms in the soil are doing cellular respiration, releasing CO2. Even if they don't have lungs, whoops, you still do cellular respiration. That's why breathing is not really the best term, but that's how we release all that extra CO2 from our own system. And then the question of once it's in the soil, why is that getting released to the atmosphere? What we saw in the last situation, right? There's a little bit extra carbon stored here. So if you remember from chemistry, last year, or 2 years ago, if you have higher density of gases, they will diffuse to a lower concentration. just because, gases like to fill the space. How is this data measured? So here's the equipment they used, infrared gas analyzers. Basically, CO2 is an absorber of infrared radiation. Infrared is what you see when you put on heat goggles, and that's actually the reason that we have the greenhouse effect. Carbon dioxide absorbs infrared and then actually jiggles a little bit and re-releases it. So basically, you can shine infrared through, um, and if you have a different amount of infrared on the other side, you know that some of it must have been absorbed by that carbon dioxide in there. And then you can therefore measure how much carbon dioxide is in the soil. And so we're going to zoom in on the little thing underneath here. So yeah, it's basically like a little, we're trying to trap the air coming out of there. So then we can measure the amount of carbon in it, carbon dioxide. Yeah, so the new ones are just totally automated, so that's why you can have it be released sort of versus trapping it, the old yogurt container. So how is this controlled? How does it increase or decrease? So depending on which organisms are doing the respiration, that could have an effect. If you have more or less plant roots, more or less fungi right in the desert, not really a lot of that, but if you go up to like Oregon or the northwestern forest, tons of fungi up there. Um, and then maybe also the types of substrates, right? If you have a more rich ecosystem, you might have more decomposition happening. You might have more respiration in that way. If you're adding more nutrients in that case, or if you have more organisms decompose or digesting that material. Let's see, and then temperature and moisture. These are actually two variables that you're going to graph, and you're going to see how that affects soil respiration. But basically, same way they affect you, right? The temperature is not warm enough, you don't want to do anything at all. And if there's a little bit more moisture in your plant, you're going to go a little crazy, do a little bit more. And then all the microbes do the same thing. I've heard, I don't know how true it is. I've heard a few things, the smell of when it rains. I've heard that it's either the ozone that comes down from the upper atmosphere, or I've also heard that the smell of rain is the microbes in the soil that come alive. Um, so one of those two things. Maybe it's the moisture controlling their metabolic rates. If there's more nutrients, huge limiting factor, as always. And then the characteristics of the soil, right? Porosity is the spaces in the soil. If there's not any spaces for the stuff to live, not going to be a lot of respiration. Let's see. So these are some of the issues that they might have with their data, which is just a little interesting. I mean, you have your normal problems like, oh crap, our software bugged out, or there was ants in our gas tubes. Classic issue. Couldn't turn my homework. Ants in the gas tube. Or some fun ones like too many earthworms in an area that are just pumping out a bunch of CO2, so it might seem like there's way more respiration happening than actual. And that's why, right, you do lots of quadrats over a big area versus just taking a few and being like, this is what's happening. You could be in a little earthworm hotspot. And then temporal variability as well. Could change day by day, right? As organisms, take advantage of warmer temperatures, and then also throughout the year, right? You might have differences in climate, and we'll actually see how that changes through the year. So here's a couple of examples of like some experiments you could do, basically. So taking multiple measurements, so we're measuring the respiration, but we're also measuring the soil temperature, we're also measuring the moisture, seeing if there's a correlation between any of those, or doing a type of experiment. So in this case, they girdled the trees, and so this doesn't allow nutrients to pass up through the tree, but allows the tree to keep standing. And that's a really important point, right? You could cut down the trees, and that would have the same effect, but then maybe the trees wouldn't have the effect of holding the soil in, and then you would kind of compound your issue. So right now, all we're doing is we're stopping the flow of nutrients. We're not stopping the roots holding the soil in place and that type of thing. Girdling's really cool. We actually did a girdling project at Prescott College. Um, there's some invasive elms that live along. That's Butte Creek, and we wanted to replace the elms with some nice willow and cottonwood. But again, there's nice birds that live in the trees, so you don't want to just cut them all down. So we ended up girdling some, um, and that way, when the tree is dead, it still is a good habitat, still provides great food source, um, and then that also allows the little baby trees to grow up at the same time. There's this little trail is going to do great now that these bigger ones will be moving out of the way. A little bit of secondary succession happening right there. And so this is sort of an example of the two graphs that you are going to strive to make here. So looking at soil respiration compared to temperature and moisture, and then running a correlation between temperature and respiration. And please do try to make sure that your temperature variable is down here, because we think it's temperature that controls respiration. It's not necessarily respiration that controls temperature. It doesn't become summer because all the soil critters start to respire. All right, good luck.